All right, now we're going to go ahead and get started with creating some Lewis structures of covalent molecules and also of some polyatomic ions. And there are many different ways of doing this. You may have learned a technique in your intro chem classes or in high school that might be a little different than what I'm showing you. Honestly, you could use any technique you want, but what I'm planning on doing is showing you the method that you are expected to use in lab number 10. So that's why I want to teach it to you this way so that you know how to fill in all the required information for that lab. Okay, so this method deals with this. S is equal to N minus A. S stands for the number of shared electrons. Okay, so if the S value is 10, that means you're sharing 10 electrons. That means you have 5 bonds. So remember, each bond is a pair of electrons. So whatever this value is tells you how many bonds you're going to have. Okay? This N is needed. Everybody wants an octet. Everybody wants an octet. So needed is always 8, 8, 8, 8, 8 for everybody except for a few of the exceptions. Hydrogen's octet is 2. Beryllium's octet is 4. Boron's octet is 6. And you'll see a couple of others also. But everybody else, the N value is always going to be 8, except for these guys. Okay? The A value is available. Basically, this is your valence electrons. How many valence electrons do you have? How many are available to do some bonding? Okay, so with hydrogen, obviously, it would be 1, right? You look up beryllium. Beryllium's in group 2A. It has 2 valence electrons. Boron has 3 valence electrons. If you look at chlorine, its available is 7, right? If you look at sulfur, its available is 6. But the N value for chlorine, 8. The N value for sulfur, 8. Okay, so those are your ground rules. Let's go ahead and get started with a couple of different molecules. All right, so let's first start off with Bf3, Boron Tri Fluoride. Okay, so our N value is needed. For the fluorines, each one of them needs 8, right? So 8 times 3, so for the fluorines, you go 8 times 3, that's 24. For boron, we said boron doesn't need 8, and boron needs 6. So we'll just put 6. So add these up, that's 30. So our N value is 30. Okay, what about available? Fluorine has 7 valence electrons. So 7 times 3 is 21. Boron, how many valence electrons does boron have? Boron has 3 valence electrons. So 3. 21 plus 3 is 24. So 30 minus 24 is 6. 6 electrons are going to be shared. So that means boron trifluoride has how many bonds? 3 bonds. Okay. Who's the central atom? You always put the element that needs the most electrons to fulfill an octet as the central atom. So fluorine only needs 1 electron to fulfill the octet. And plus, by the way, fluorine is never a central atom, just like hydrogen is never a central atom. Okay? So we're going to put the boron in the middle, and we're going to put 3 bonds, and we're going to put the fluorines all around. All right. How many did you just use up? You just used up these 6, right? So do we have other electrons remaining that have to be shown in the Lewis structure? Yeah, remember, the whole point of a Lewis structure is to show all the electrons in the molecule, show which ones are bonding and which ones are non-bonding. Okay, so we already know that there are 6 bonding electrons. Where are the other electrons? How many non-bonding do we have? So what you do is you take this value here, 24 minus 6. So basically, your available minus the ones that you shared. So 24 minus 6, you have 18 electrons. What do you do with the 18 electrons? You distribute them. You always distribute them around the periphery first, and then anything that's left over, you dump on the central atom. All right, so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We are completely done with all 18. So this here is the Lewis structure of boron trifluoride. Okay, let's do another one. We're still going to use S is equal to N minus A. Let's do carbon dioxide. Okay, carbon dioxide. Crunch the numbers. N value, remember, everybody's 8 except for the ones that I told you aren't 8. So 8 times 3 is 24. A value, carbon is 4 because it has 4 valence electrons. Oxygen is 6 times 2 is 12. So 4 plus 12 is 16. Okay, so 24 minus 16. And we get 8. What does 8 mean? 8 means that you are sharing 4 pairs of electrons. That means you have 4 bonds. So who's going to be in the middle? The element that needs the most electrons to fulfill the octet, which is carbon. We are going to need 4 bonds, so we're going to put 2 on one side, 2 on the other side, put an oxygen here and an oxygen here. Good. So how many left do we have to distribute? Remember what we do. We take the A value minus the S value. So for the remaining electrons, you take your A value minus S. Okay? So 16 minus 8 is 8. Let's distribute the 8. Now they have to be distributed in pairs around the periphery. Okay? 1, 2, 3, 4. Why don't I put 5, 6 over here? Because this already has 8. 2, 4, 6, 8. This one's completely happy. So 1, 2, 3, 4, 5, 6, 7, 8. This has 8. This has 8. This has 8. Perfect Lewis structure for carbon dioxide. Okay, let's do another one. Here's a bit of a tricky one. Nitrite. Okay, anytime you have a polyatomic ion, you have to include the charge in the A value, in the available value. All right, so remember, S is equal to N minus A. What is the N value? Everybody's 8. Everyone's 8. So the oxygen is 8, the nitrogen 8, that's 3 of them. 3 times 8 is 24. Now what about the available? Nitrogen is 5 valence electrons. Oxygen is 6 times 2 is 12. And then I have to add this. I have to add 1. Anytime you have a charge, let's say the charge is minus 2, you add 2 electrons. If the charge is minus 3, you add 3 electrons. If the charge is plus 1, you subtract an electron from the available value. Okay? So this is 18. 24 minus 18, and you have 6 shared electrons. If you have 6 shared electrons, that means you have 3 bonds in this molecule. So which one are we going to put in the middle? The nitrogen, because the nitrogen needs the most electrons to fulfill the octet. What if 2 elements need the exact same number of electrons to fulfill the octet? Then you put the less electronegative one in the middle. Like if you have a sulfur and an oxygen, in the case of sulfate or sulfite or sulfur trioxide, you put the sulfur in the middle because even though the sulfur and the oxygen need the exact same number of electrons, sulfur is less electronegative, it goes in the middle. Okay, so we're going to put the nitrogen in the middle because it needs more electrons to fulfill the octet. And it says here we need 3 bonds, so we're going to have an oxygen on this side and an oxygen on this side, and that means we're going to have a double bond somewhere, so either on this side or this side. Okay, so how many did we use? We used up 6. How many were we given? We were given 18. So 18 minus 6 is 12. We have to distribute 12 electrons. Where do those 12 electrons go? They go on the periphery in pairs so that everybody gets an octet. And then if you have any left over, you dump them on the central atom. So you go 1, 2, 3, 4. This has 8 already, so we're done. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where do 11 and 12 go? Right here on the middle. Anytime you have any electrons that are extra, you dump them immediately onto the middle. Okay, so this is the Lewis structure of a polyatomic ion. Usually we put brackets around it and we put a charge. This is also a good place to introduce the term resonance. Resonance, you're going to be seeing that in organic chemistry and biochemistry, but you also see it in Gen Chem when you have molecules that have double bonds and the peripheral atoms are identical. Like, what made me decide to put the double bond here? Why didn't I put it over here? Because it doesn't really matter. It's on both sides, should be fine. And actually what happens is that this double bond just keeps moving. It resonates. You actually have both scenarios existing. So you have something like this and like this. This is a resonance. It just the double bond resonates from this side to this side to this side to this side. And you can never know exactly where it is, because when you measure the length of this bond and this bond, they're the same. Even though double bonds are usually a little shorter than single bonds, but they're the same because it just keeps moving. So you can't ever tell where it is. All right. But when you're doing a Lewis structure, it's fine to just draw one of them. If you draw both of them, you could draw an arrow saying, they both go from here to here. Okay. In the next video, I'm going to introduce exceptions to the octet rule. We're going to do molecules that carry more than 8 electrons around the central atom. Remember, all of these had 8, or with the case of boron, it had 6 because its octet is 6. But you're going to see molecules that have central atoms that are in the 3rd period and 4th period, meaning they've got a D zone that they could use. So they can have exceptions to the octet rule. Any elements that are in the 1st or 2nd periods can't have that type of an exception. You can't carry more than 8 because there's no D zone. But the minute you get into those lower periods, or the period 3, period 4, period 5, anytime you have one of those there, you can have those exceptions, and you'll see that in the next video. Okay, good. And honestly, the only way to get really, really good at this is to just practice. The more you practice, the easier it is. And it becomes really important in this chapter, and also obviously in chapter 10 too, when we talk about molecular shapes and all of that. Because you're going to have to do a Lewis structure before you do the molecular shape. Okay, let's get started on the exceptions to the octet rule in the next video.